Hello, I'm John Fitch, MIT science reporter. We're at MIT's Lincoln Laboratory in Lexington, Massachusetts, a major research organization which has played an important role in developing this nation's defense system since World War II. And although Lincoln Laboratory is perhaps best known for its work in radar and advanced warning systems, it has also seen the beginning of the computer era and has made many important contributions to it. To learn about some of its recent work in improving the relationship between man and this important machine, we talked with Professor Stephen Coons, an associate professor of mechanical engineering at MIT and co-director of the Computer-Aided Design Project.
John, we're going to show you a man actually talking to a computer in a way far different than it's ever been possible to do before.
Surely not with his voice.
No, he's going to be talking graphically. He's going to be drawing, and the computer is going to understand his drawings. And the man will be using a language, a graphical language that we call Sketchpad, that started with Ivan Sutherland some years ago when he was busy working on his doctoral degree. And you will see a designer, effectively, solving a problem step by step, and he will not at the outset know precisely what his problem is, nor will he know exactly how to solve it. But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how does this differ from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with a computer has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant. And the computer will seem to have some intelligence. It doesn't really, only the intelligence that we put in it. But it will seem to have intelligence. In the old days, to solve a problem, it was necessary to write out in detail on a typewriter or in punch card form all of the steps, all of the ritual that it takes to solve a problem.
Because the computer is so literal-minded?
Because it's very literal-minded. If you, for example, in the old days, made so much as one mistake of a comma in the wrong place or a decimal point that was omitted, the entire program would hang up and wouldn't run. But nowadays, if you make a mistake, you can correct it, as you'll see, immediately, and the computer is much more tolerant and much more flexible.
We met next with Mr. Timothy Johnson of the Design Division of the Department of Mechanical Engineering and asked him to show us this computer and its Sketchpad.
We're at the TX2 console at Lincoln Lab. This machine, a large computer, was built by Lincoln Lab in 1956 as a research machine.
Now, how does this differ from a computer that would be used to run your bank account or something like that?
Well, it's designed specifically for a study of manual intervention, where the man can command the computer to take different courses of action while the program is running. You can see we have several unusual pieces of input-output equipment here. We have a scope, a knob. These are unusual at the time, and push buttons, toggle switches. We have several other related devices. This made the TX2 a prime candidate for the Sketchpad developments back in 1961, and it remained a program in this machine, so it would become a coherent partner in graphics, so the man can communicate with the machine.
Now, how do you actually go about communicating with a computer in a graphical sense?
Well, we are using an oscilloscope here, which is much like a TV set, except it's being driven by the computer. In order to get the information into the computer, we have to draw somehow on this display, and we use the light pen. Well, in order to construct a meaningful engineering drawing, we have to have several graphical manipulations. Sutherland's programs can draw straight lines and circles.
Well, that's about what you do in the drafting equipment anyway, isn't it?
That's a very good start.
T-square.
In order to do this, we can position this bright spot in the middle of the cross that you notice at a desired location. And we press the button to command the computer to draw a line. It will draw a line from this position, where I am now, to any subsequent position of my light pen. This is much like a rubber band stuck on two pins. One is nailed on the screen here, and the other is at my light pen. So I can position this anywhere I want. Now, I lost tracking there. I moved the pen too fast, and that told the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it.
Well, the dot in the center of the cross, when you get close to the line, jumps over onto it.
Correct.
Why does it do that?
It's much like a gravity field. At the end point, it is even a higher gravity field to allow us to position the point exactly on the line, or in this case, exactly at the end point. This allows me to move my pen quite coarsely, be sloppy while I'm drawing, and get a precision drawing out at the same time. So now I'm going to draw a second line.
Yeah.
And even a third one. Now, in an ordinary pencil and paper drawing, all we have is this particular picture. But the computer understands the geometry of the drawing here. What do I mean? I mean that if I point at this particular point and tell the computer to move that point by another push-button command, it will move not only that point, but all three lines that are attached to it.
And the delay between it's doing what you want it to is because it's computing all these changes.
That's correct. Now, if I made a mistake, I could delete my mistake by pointing at the line in question, for instance, and pressing the appropriate button. It's gone. Now, I mentioned before we could draw circles also.
Right.
In order to do this, I must first indicate the center of my circle. Let's choose it to be here. And then I'll move out to an initial radius, let's say this point right here, and I press the second button to start drawing the circle. Here's our circle. Let me reduce the drawing slightly so our circle shows on the computer scope. And you see as I move the pen, it is ignoring the radial position. I've just gone off the scope screen here. The radial position of the pen and only looking at its angular position. So I can
be very as sloppy as you like, in other words.
Right. In other words, the computer has supplied the compass here, much like as it supplied the straight edge for the straight line.
If you go backwards, you erase it.
And I can wind it up the other way. Now, if I tell the computer to put that point right at this circle, right in that point right there, the computer knows that those must be connected. It turns out that they're not really connected. It's a very small nub there. Let me move this away and show you that they're really not connected.
I see.
But I have told it by terminating the point of the pen at that position that it must be connected. Now, I can tell the computer to satisfy this constraint command by bringing in a program under command of this toggle. And watch the scope. You see now that indeed the circle is ending at that line. We have constrained the drawing to behave this way.
Well, now, I wonder if you'd expand a little more on this idea of a constraint. Just what do you mean?
All right. Let me go to a second piece of paper. Now, what I've done here is I really saved away that drawing I just drew.
You can get it back again?
I can get it back, and I can select my drawing number by these toggles here. So I've selected a blank piece of paper, we'll call it. We have several pieces of paper. And I can, let's say I'm beginning to design. I have a very nebulous idea what I want to have in mind. Now, as I draw my part, let's say on the scope, it reinforces what I have in mind. This is, in general, part of the design process. And as I apply design criteria, stresses, and so on, eventually I will know what the exact shape of this part is. I shouldn't be required to draw the exact shape at the beginning. I really don't know what it is. But let's say I've decided eventually in this model that I want these to be horizontal and vertical, a box. I can apply a new constraint, a horizontal constraint here, and a vertical constraint here, and a horizontal here by pointing at the line and pressing a button. Well, now, nothing has happened yet because, remember, I still must tickle that toggle over there to command the computer to satisfy these constraints.
So you won't actually let those rubber bands relax then until you say so.
Right. And I'll do that, and watch again. There we have a box.
Well, now, this idea of having constraints like this, being able to make lines meet or to make them horizontal or vertical, makes it quite a step ahead of something that's just a drafting machine that allows you to draw, doesn't it?
Exactly. In other words, you can get the topology down of the part, and at any subsequent position in your design, you can make it to behave exactly what you want. Straighten the drawing up. In other words, you don't have to draw exactly at the beginning like you have to do in drafting. This is, of course, just one aspect of the program. Now, what I can do, in addition to this, is call up copies of master pictures. Remember that picture we drew before?